Hello, welcome to my YouTube channel. In the first lesson on physical quantities, I talked about the meaning of physical quantities, the various types, and the units of base quantities in the SI unit system. And I told you that today we're going to talk about units of derived quantities and transformation of units. And in our lesson outline of today, we're going to talk about how to obtain units of derived quantities. And then we'll give some examples on that. And then we'll discuss prefixes to unit names and symbols in the SI unit system. And finally, we're going to do examples of transformation of units. How to obtain the units of derived quantities. Now, we are going to talk about dimensional analysis very soon. And dimensional analysis is a technique that is used in physical quantities, and it has so many uses. And one of the importance of dimensional analysis is that it helps in recapitulating important formulae. And this is very important. The reason is because to obtain the unit of a derived quantity, the very first thing is that you have to know an equation or formula that defines that physical quantity or any other equation in which the quantity is a part. So you must know an equation that defines the derived quantity or any other equation in which the quantity is a part. And then you make the derived quantity the subject of the formula if it is not already. And then finally, you insert the units of the other quantities in the equation and simplify your result. Then you will get the unit of your derived quantity. Okay, so let's see how we can obtain the unit of some derived quantities. We have a table then given to us with four derived quantities. Speed with equation distance divided by time taken, acceleration with equation change in velocity divided by time taken, force with equation mass times acceleration, and charged with equation current times time. So let's see how we can use these equations to obtain the units of the various derived quantities given to us. Starting with speed, speed is distance divided by time taken. So the unit of speed is unit of distance, which is meters, divided by the unit of time, which is seconds. And that gives us meters per second. Or if we can use indices, the second in the denominator can go up and we have it this other way. Unit of acceleration. Acceleration is change in velocity divided by time taking. So whether it is as a velocity or change in velocity is the same thing. They have the same unit. So we have meters per second for change in velocity divided by the unit of time, which is seconds. And if we change the division sign to multiplication, we can have the second written in this other way. And meter times meter will give us meter, while seconds times seconds give us seconds squared. And same like we have done with speed, if we can use indices, the second squared can go up and we have it this other way. Unit of force. Force is mass times acceleration. So the unit of mass is kilograms, while the unit of acceleration is meters per second squared. And if you multiply the two, we have kilogram meters per second squared. And this is what is usually called the Newton. And you see the way we have written the SI unit Newton, starting with small letters. You know, whenever the name of a scientist is used as an SI unit, it always begins with a small letter, a lowercase letter, to differentiate it from the name of the scientist. Lastly, we have a unit of charge. Charge is current times time. So the unit of charge is a unit of current, which is ampere, times the unit of time, which is seconds. And that gives us ampere second. And the combined unit that is used for ampere second is the coulomb. Again, it starts with a small letter C. Okay, so I think this was really interesting. Let's take some other four. So let's see how to get the unit of four other derived quantities. Starting with pressure. Pressure is force divided by area. Work done. Work done is force times distance. Potential difference. Potential difference is work done divided by charge. And finally, inductance, which is EMF divided by rate of change of current. So starting with pressure. The unit of pressure should be equal to the unit of force divided by the unit of area. Now we're just going to use what we have obtained for force. But if you are asked in a test to get a unit of pressure, you need to first of all show how to get a unit of force. So we'll just use it now because we have already derived it. So the unit of force is kilogram meters per second squared divided by the unit of area. Area is length times width. Length and width are both distances, and distance is measured in meter. So the unit of area will be meter times meter. 1 meter in the numerator cancels 1 meter in the denominator, and we can use indices to remove the other meter in the denominator, and we're going to get kilogram per meter per second squared. And that together is called Pascal or Newton per meter squared. Unit of work done. Work is force times distance. So the unit of work done should be the unit of force times the unit of distance. Kilogram meters per second squared times the unit of distance, which is meters. The 2 meter multiplies and we have meter squared. So the unit of work is kilogram meter squared per second squared. And all of that is called joule. You should note that the unit of energy and the unit of work done are the same. So in a situation where you are asked to find the unit of energy, please use the same method that we have done for the unit of work done. Unit of potential difference. Potential difference is work done divided by charge, and we have already obtained it. And we're going to use it because we have already obtained it. In a situation where you are asked to find the unit of potential difference, then you need to first of all show how to get the unit of work done. So we're going to use it kilogram meter squared per second squared divided by ampere second. And indices can be used to remove ampere and second from the denominator. And we have kilogram meter squared per second cube per ampere. And that together is called joule per coulomb or simply volt. And you should note that the unit of EMF and the unit of potential difference are the same. Unit of inductance. Inductance is EMF divided by rate of change of current. So we'll just use what we have obtained above. Kilogram meters squared per second cube per ampere divided by ampere per second. Rate of change of current with respect to time is like taking current divided by time, which is ampere divided by second. So we have ampere per second. And using indices to remove the ampere and the per second from the denominator and simplifying, we get kilogram meter squared per second squared per ampere squared. And that together is called Henry. Okay, so we have this other exercise to determine the units of G, the universal gravitational constant. And we have the equation, but G is not the subject of the formula. So the first thing is to make G the subject of the formula, and that will give us G as FR squared divided by M1, M2. And then since we know the unit of force, R is distance, so the unit is meters. M1 and M2 are masses, so their units are kilograms. So if we just substitute and cancel 1 kilogram in the numerator and the denominator and simplify, we get per kilogram meter cube per second squared. And there is this common mistake that students usually do by equating a physical quantity to the SI unit. Please, it is wrong. It is meaningless. Never equate a physical quantity to the SI unit. So you cannot say velocity equal to meter per second. No, it's wrong. Instead, you should write unit of velocity equals to meters per second. That is the right thing. Okay, so I couldn't treat lesson 2 all in one piece, so I've divided it into part 1 and part 2. Part 2 of the lesson will be on prefixes to unit names and symbols and examples on transformation of units. So that will be coming up soon. I would like that you subscribe to be notified when the next video drops. Thank you. This is Physics with Omia.